Hi guys. In this video, we are going to talk about the method of characteristic in solving for first order PDEs in general. Right. So we have a first order partial differential equation. I want to solve it using the method of characteristic, and this applies to general first order differential equations, not only homogeneous transport equations without decay. Initially the ones we had, example, maybe ut plus your cux is equal to 0. This was very simple to solve. We got to know that the function, the solution xt was equal to the function at a certain constant s, where the constant was x minus ct, right? Yes. So you can see this homogeneous, and there is no decay term, right? There is no interactive. So this became simple for us to solve, all right? But here's the situation where we have interactive terms. We have -3. There's a decay term. There's your inhomogeneous term. So with a question like this, how do we solve it? So if we're able to look for a general way of solving first order differential equations, then we can apply that over here. All right, so we are just going to use this example to explain the method of characteristic over here. All right, so anytime you're given a question, no matter how it may look like, once it's a first order PDE, you can apply the method of characteristic, and you'll be able to find the solution to it. Now, the other method of solving these first order PDEs is the change of coordinates, and we are going to do that in our next video. You're going to look at the ways of solving, or how to solve the first order PDEs with the method of change of coordinates. So let's move on to the method of characteristic. How we are going to solve this equation, or this partial differential equation, with the method of characteristic, and this is how we do it. This is how we do it. Now, we actually see that our function u is a function of one space variable x and another space variable t, right? And there's the in decay term, and this is your inhomogeneous term, all right? Yes. Now, in PDEs, most partial differential equations are unsolvable in their partial form, right? So this is actually unsolvable in its partial form. If you try to use normal partial integration, you aren't going to be able to solve it, right? So one thing you can do is to break this down into an ordinary, or a system of ordinary differential equations. Then you solve them one after the other. You do necessary substitutions, then you can solve it. So the main thing you are doing here is to break this down. This PD you have here, you're trying to break this down into an ordinary differential equation, then you can solve it. Okay, so once you solve the ODE, or the partial differential equation, then it means that you can substitute back the parameters, or the variables you have here, back into the solution to the ODE. Then that becomes the solution to the PDE, right? Yes. So now, without further ado, or without much ado, I'm going to head on to the solution. So what we first do is to parameterize. We parameterize um we parameterize the terms over here, ux and t, with respect to, or we parameterize it with respect to a different variable. So we parameterize the oh let me write it a bit down. So we parameterize the variables with respect to any variable you can think of. So with respect to any variable, so let's say I'm choosing m. Okay. So this is what we're gonna do. If m is our new variable and we assume that we are parameterizing the variables x and t with respect to m, so it means t is a function of m and x is also a function of m. That's what we are trying to say, right? And u2 is going to be a function of m and another variable, so that new variable is going to be an s or anything or any variable you can think of, but we are not there yet, so let's move on. So that's what we're going to do. We can write this as a differentiation, and that differentiation is going to yield a chain rule, right? So after parameterization, we are going to head on to a chain rule process. So this is what we have. We have m, t depends on m, x depends on m. So it means invariably u depends on m as well, alright? So now we are trying to differentiate u with respect to m, right? And since u is a function of t, which is also a function of m, we'll first have to differentiate u with respect to t. Then we multiply it by the differentiation of t with respect to m. Then you do the same thing at this point, right? You differentiate u with respect to x, then you multiply by differentiating x with respect to m, right? So let's do that over here. So I have d u dm being equal to del u del t multiplied by del t del m, right? Plus del u del x multiplied by del x del m. Alright? Yeah, so that's what we have. So if that's what we have, we know del u del t to be u subscript t, differentiating your u with respect to t, alright, or differentiating your u with respect to t. And this actually is your coefficient of the derivative of u with respect to t, right? So it means your del t del m is going to be equal to 1, right? So let me write that one here. Del t del m is equal to 1. Then I do the same thing for the other one. Del u del x is actually u subscript x, right? So your del x del m becomes 1 as well, right? So I have del x del m is equal to 1. Okay, now doing your normal partial integration or doing your integration, you have integral del t being equal to integral del m. So which means that t as a function of m, t as a function of m, t as a function of m, because we are parameterizing t with respect to m, right? And that is going to be equal to m plus an arbitrary constant. So I'm going to call that arbitrary constant s, not s. It could be c, it could be anything. So I'm calling that s, right? Yes. Now I do the same thing for this too, and you realize that I have the integral of del x. That's going to be the integral of del m, right? So I have x of this m being equal to another m plus s. Okay? Yes. So now when we go to our initial conditions, we want to see the value of t, alright? We want to see the value of t and x at a general point, let's say the origin. So when m is 0, what's going to be the value of t? And when m is 0, what's going to be the value of x? Okay, so we go to the initial conditions and we see that x is always varying irrespective of the value of m, because x is x, right? But t is 0 everywhere, so it means that no matter the value you're going to put here, even 100 or 200, your t is always going to be 0, alright? So we picked a common point, and our common point was when m is equal to 0, right? So we see that t at 0 is going to be 0 plus s. And we already know t from our initial conditions that t is 0, right? So it means 0 is going to be equal to s, so s is equal to 0. Okay, yes. But since x is always varying, whatever value you're going to put here, x is going to vary, so you don't touch this. This is going to be just x is equal to m plus s, all right? You don't touch it because x is always varying. X is varying. There's no constant value that it has that you can look for, okay? Yes. So s is 0 over here, so you can actually simplify this and get t being equal to m. So this implies that t is equal to m. All right, yes. So now that we have these two, we have all these two, right? We have these two, right? Yeah. T is equal to m. So if I want to make x s the subject over here, this is one new variable, so the other one is going to be this actually a constant, but in terms of u, it is going to be a new variable, right? So let me make that a subject and see that my s is actually a constant. So let me put that way, it's a constant. So that constant is what? X minus m. Okay, yes, and we know m to be equal to t, so I can write s being equal to x minus t. The reason why we are doing this transformation is that in the end, our du dm, or our solution u here, we have du dm, right? So our function that we are going to get is going to be a function of m and s, right? So we have to know m and s in the in terms of our old variables x and t. So that's why I'm trying to make all the new variables the subjects. Okay, yes, so my m is equal to t and my s is equal to x minus t, right? Yes. So now let's see, we replaced all these things over here with du dm. So it means that this whole left hand side is going to be just du dm. All right, so let's do that substitution. So it means that from our general equation we have du dm minus 3u, and that is equal to t, right? T, right? But let's look at something. We are going to integrate with respect to m, not t. So it means that we have to look for the corresponding the t. What does t represent in the m and s coordinates, right? So t is equal to m over here, right? So I have to do that substitution over here as well. So t, instead of writing t, I'm going to write m, because I'm going to integrate with respect to m, and so my t is not going to be used here. So I have to come back to my m, right? So that's what I have. Okay, yes. So now this is a first order ODE. So let me shift a bit. This is a first order ordinary differential equation, right? Yes. So that's it. So if it's a first order differential equation, then we can solve it ordinarily, right? Yes. So anytime we have something like this, we can find the integrating factor of this whole differential equation, which is going to be e to the power the integral of the coefficient of u. All right, yes, so we do that, then we find the integrating factor. Once we have the integrating factor, we can multiply each term here by the integrating factor, then we can break it down. It becomes simple to solve. All right, so my integrating factor is going to be equal to e to the power negative of 3 and dm, because our integration is going to be with respect to m, right? So this is actually going to be e to the negative 3m, right? Yes. So now what we are going to do is to multiply each term here by e to the minus 3m. So I have e to the minus 3m u dm minus 3e to the minus 3m times u, that should be equal to, that's going to be equal to m e to the minus 3m. That's what I'm trying to do. Right? Yes. So take a very good look. Take a very good look at this part, right? Taking a very good look at this, the left hand side of the equation. See this, you're differentiating u with respect to m, and you are maintaining e to the negative 3m, right? And just look at this, you are maintaining u and you are differentiating what? E to the negative 3m. Okay, so this actually tells us that it was actually a differential or a derivative of a product, right? And we all know this from our ODE. So this is a derivative of a product we know, right? So what is going to be that product? It's going to be u and e to the negative 3m itself, because we are differentiating u and maintaining this. We are differentiating this and maintaining u here. So the main function, the main terms here are u and e to the negative 3m. So it means that the left hand side is the derivative with respect to m of the product of e u e to the minus 3m over here, right? And that should be equal to m e to the negative 3m, right? All right, very good. Let me do some cleaning over here. Okay, sorry. All right, so that's what we have. That's what we have, right? So we can now do our integration, and our integration is going to be like this. We have du e minus 3m is going to be equal to m e to the negative 3m dm, right? So we have to integrate this side and integrate that side. Okay, yes. So how is the integration going to look like? So by integration by parts, let me do that down here quickly. I want to do that down here quickly. I'm going to use the short method. I'm going to choose my u and dv. So this is my m, this is my e to the negative 3m. So I differentiate m, I get 1. I differentiate 1, I get 0. I integrate this, I get negative 1 out of 3 e to the minus 3m. I integrate this again. And I'll be getting 1 out of 9 e to the negative 3m, right? Yes. So now that I have these, I know that I'm going to multiply this and I multiply that, the 2. This one's going to be a positive multiplication. This is going to be a negative multiplication. All right. Yeah. So now let's just finish that up on the left hand side. So this actually means that I'm going to get u e to the negative 3m being equal to the integral of this. We know how to integrate by parts. So this is going to be negative 1 out of 3m me minus 3m. Oh my god. Then minus again, because this is plus, this is minus. So minus 1 out of 9. What do we have? 1 out of 9 e to the negative 3m, right? Yes. So that's what we have. So I can clean this. Let me clean this so that I'll have some space. So plus a constant, right? Yes, it's supposed to be a constant. But we know u not to be only a function of m. It's supposed to be u of m and another variable, right? So that variable here, when we were trying to do integration over here, we chose our arbitrary constant to be s. So the s becomes the other variable of the u. So u becomes u of s and m, right? Yes. So since I integrated with respect to m, it means I kept all x's constants, right? So it means it's going to be added to a function of s, right? It is a partial integral. It's a partial integral because u is not only a function of m, it's a function of m and s. So if I want to add s to it, I can't just add s. That makes it just an arbitrary constant. But in partial differential equations, your integrations should yield arbitrary functions, not arbitrary constants. All right, so that's what we have here. All right, so now let's move on. Let's move on. Let's move on. So, oh my God, what's wrong with this? I'm sorry. Come on. Oh no. Okay, so I can actually divide through by e to the negative 3m, this to the negative e to the negative 3m, e to the negative 3m, then e to the negative 3m, right? Yes. So now that I'm done, I know this will cancel that, that goes with that, that goes with that, right? Yes. So I'm gonna be left with, oh my God, what are all these things doing here? I'm gonna be left with something like this. Sorry, let me clean all these things. I'm gonna be left with something like this. All right, so I have u of Sn being equal to, u of Xn is going to be equal to 1 negative 1 over 3m, sorry. What are all these things doing here? Negative 1 over 3m, negative 1 over 3m, negative 1 over 3m minus 1 over 9, minus 1 over 9 plus f of s. Then when you bring the denominator to the top, you have e to the 3m, right? So e to the 3m. Am I right? Let me see, let me check. Yeah, I have e to the 3m. Okay, so that's what I have, u of Sm. So this is actually a solution to the differential equation. But the differential equation was given in terms of x and t, not s and m. So it means you will have to change this back to its normal differential equation, its normal coordinates. So you have u of xt being equal to negative 1 over 3. Now you go back to your transformation and see what m was. So what was m in terms of x and t? M is equal to t. So I have minus 1 over 3t. Then I have minus 1 out of 9 plus f of s. So what was s there? That was x minus t. So x minus t. Then e to the 3m was t. So this is what we have as our general solution. So this is our general solution. So this is a general solution to the partial differential equation. Then we can go back to our initial conditions. So with our initial conditions, we had u of x0 being equal to s squared. Then with the initial conditions, you have, this is what you're going to have. You have u of x0, and wherever you see t, it means you're going to put 0 over there, right? Yes, so it means that at this point is going to tend to 0 because negative 1 over 3 times 0 gives you 0, minus 1 over 9 plus t is 0, so we get an f of x over here, then e to the power 0, right? So this is going to give you f of x minus 1 out of 9, right? And in your initial conditions, you have u of x0 being equal to x squared. So this one is equal to x all squared, right? Isn't it? So to make f of x the subject, if you make it the subject, you have f of x being equal to x squared plus 1 divided by 9, right? Yes. So what is the arbitrary function over here? F of x minus t. So this is what we do not know, but we know the mapping from x to its codomain. So if I know f of x to be equal to that, then I can look for f of x minus t. So f of x minus t is going to be x minus t squared plus 1 divided by 9, right? Yes. So once I have these, I can plug it back into this equation, right? And that becomes my solution. So u of xt becomes negative 1 over 3t, negative 1 over 3t minus 1 over 9, minus 1 over 9, then plus I have all these multiplying e to the 3t, right? So I'll be getting all these x minus t all squared plus 1 over 9 multiplying e to the power 3t. So multiplying e to the power 3t. Alright. So this is the solution to the differential equation you have here. So this is the solution to the differential equation you have over here. Right. Yes. So you can further do some simplifications. You can bring 1 over 3 out, then simplify this, or you can leave it like this and you are correct. So this is how we use the method of characteristic in solving first order partial differential equations of any form. When you apply this method of characteristic, you'll be able to solve that PDE. Once it's first order differential equation, you should be able to solve it with that. All right, so first of all, you have to do your parameterization, then you do your transformations, then you solve the ODE you get after your transformations. Then after solving them, you try and turn them back into your x and t. Then to find a general solution, you use your initial conditions to find the initial conditions and to find a general solution. So this is how we go about by using um, 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 method of characteristic in solving the first order partial differential equation. So in our next video, we are going to see how we use the method of characteristic in solving partial differential equations with variable coefficients. You see, all these have constant coefficients, right? So the coefficients are constant. But in our next video, we are going to solve questions which have variable coefficients. Coefficients are variable, all right? Yes. So in the next video, and in the next video, we're going to talk about that. All right. So peace. If you like my content and you see it as useful, please like the video and subscribe to my channel for more videos. All right. See you.